everyone, and many thanks to the organizers for inviting me for this presentation. My name is Tiffany Vass, and I'm an industry analyst within the Energy Technology and Policy Division at the International Energy Agency. In my presentation, I will provide an overview of our analysis on what is needed to get the industry sector to net zero emissions. As many of you may already be aware, last year the IEA released its Net Zero by 2050 roadmap for the global energy sector. My presentation today will be based on the results of that analysis. This analysis was conceived in the context of many government and company announcements to reach net zero emissions by the year 2050. Some countries aim to achieve this target earlier, some a bit later, but 2050 is increasingly becoming the target year around which climate ambition is measured. One of the key components of our analysis is a series of detailed milestones, more than 400 in total, which can help governments see the scale of the challenge ahead of us. To provide just a few examples, annual solar PV and wind provide around 40% of electricity generation globally in 2030, up from 9% today. Electric car sales must rise to about 60% of total sales by 2030, compared to 5% today. By 2035, there are no new sales of internal combustion engine vehicles globally. With regards to buildings, 20% of the existing stock globally must be retrofitted to be zero carbon ready by 2030, compared to less than 1% today. So what does net zero by 2050 mean for the industry sector? Essentially, there is no refuge for emissions in the net zero emissions by 2050 or NZE scenario. Every sector must play its part, and the industry sector is no exception. Furthermore, it is too large to be entirely offset by carbon removal technologies in other sectors. Industry emissions account for about a quarter of global energy system emissions today. Three heavy industry sectors, steel, cement, and chemicals, which produce materials that play a critical role in our daily lives, account for around 70% of the emissions from the industry sector, and these emissions are some of the most challenging to tackle. There are several reasons for that. Heavy industry sectors use large quantities of fossil fuels for generating high temperature heat as a feedstock and as a reduction agent. The problem is that fossil fuels provide these energy services so well and so cheaply. Directly substituting fossil fuels used for these purposes in heavy industry with electricity at the scale required is impractical or expensive in most instances today. Industrial process emissions also pose a challenge, as they cannot be eliminated simply through fuel switching. Because of these technological challenges, technologies that can achieve substantial emission reductions in the production of these materials tend to be at an earlier stage of development or technology readiness than in the power and passenger transport sectors, for instance. Here we are talking primarily about carbon capture and storage and hydrogen technologies, but also direct electrification technologies such as iron ore electrolysis and electrified cement kilns. Additionally, the very nature of industrial production and markets adds to the challenge. The ease with which many industrial materials and products can be traded globally means that markets are competitive and margins are low. This leaves little room to absorb additional costs stemming from the adoption of more expensive production pathways in the absence of mechanisms to create a level playing field for them. Also, heavy industries use capital-intensive and long-lived equipment, which slows the deployment of innovative low-emissions technologies. In the net zero by 2050 scenario, stakeholders overcome these challenges and CO2 emissions from the industry decline by nearly 95% by 2050. The energy mix in industry changes radically in the NZE. The share of fossil fuels in total energy use declines from around 70% today to 30% in 2050. The vast majority of fossil fuels still being used then are in heavy industries, mainly as a chemical feedstock or in plants equipped with CCUS. Electricity is the dominant fuel in industrial energy demand growth, with its share of total industry energy consumption rising from about 20% today to 45% in 2050. Some 15% of this electricity is used to produce hydrogen. Bioenergy plays an important role, contributing 15% of total energy use in 2050, but sustainable supplies are limited, and it is also in high demand in the power and transport sectors, which limits higher levels of uptake in industry. Now let's go deeper into what is needed for the industrial sector to align with the net zero emission by 2050 pathway, focusing specifically on the challenging emissions from heavy industry. An array of mitigation strategies are needed. In the short term, much of the emissions cuts will come from incremental improvements within existing technologies. This includes improving energy efficiency and material efficiency. These two strategies account for around half of emission reductions to 2030 in the scenario. In the longer term, incremental strategies will be insufficient on their own to achieve the deep emissions cuts required in the net zero by 2050 scenario. Innovative technologies will be needed. Here, carbon capture and storage and hydrogen play the largest role, contributing around 50% of the emissions reductions in heavy industry in 2050 in the NZE. These technologies enable the provision of large amounts of high-temperature heat, which in many cases cannot be easily provided by electricity with current technologies, and help to reduce process emissions from the chemical reactions inherent in some industrial production. As a consequence, we see a large role for technologies that are not yet market-ready, with technologies that are at the demonstration or prototype stage today accounting for nearly 60% of emission reductions in 2050. Besides the strategies already mentioned, fuel shifts from coal to gas and use of bioenergy and electricity also play a role, the latter two in particular for ancillary processes where low temperature heat is required. Now let's focus in on a few of these strategies. Material efficiency is an important strategy in the NZE by 2050 scenario, accounting for about 20% of emission reductions in 2050. In the NZE, global demand for materials remains robust due to continued economic development and population growth. However, material efficiency helps to curb growth in demand, in turn helping to lower emissions. Taking steel as an example, opportunities for more efficient use exist across the value chain, from the steel manufacturing plant to downstream designers and manufacturers, all the way to the use and end-of-life phases. In the net zero emissions by 2050 scenario, steel demand is increased through building clean energy infrastructure. This includes demand from particular end-use segments, that is the power sector, which has about 3 times higher demand than in the baseline projection, and rail infrastructure, which is about 1/3 higher. However, these segments account for a relatively small share of total end-use steel demand to begin with, and the increases are far outweighed by the combined impact of demand reduction through material efficiency. A portion of the demand reduction occurs by reducing scrap generation during manufacturing. A much larger contribution is made by changes in the design and use of steel products. For example, the single largest contributor to demand reduction is extending the lifetime of buildings. Many buildings are currently demolished before the end of their technical lifetime, and so taking the opportunity to refurbish and repurpose these buildings leads to a considerable reduction in material demand. In the vehicle supply chain, contributions come from lightweighting and reductions in vehicle sales driven by mode switching. Together, these strategies result in steel demand that is 20% lower in 2050 compared to a baseline trajectory. Additionally, increased recycling helps reduce the amount of more energy-intensive primary production that is needed. But of course, material efficiency can only get us part of the way, and so the remainder of production must be produced with near-zero emission methods and technologies. As mentioned, many of such technologies for heavy industry are not ready for market and thus require rapid innovation over the next few years to get them ready for deployment. In the NZE scenario, earlier stage innovative technologies grow from just a handful of mainly demonstration and pilot scale plants today to account for around 10% of total heavy industry output by 2030 and 95% by 2050. To reach this 2050 target would require that nearly all capacity additions are innovative near-zero emission routes by around 2030. The specific near-zero emission technology profile differs by material. For chemicals, we see a large role for carbon capture and storage due to its more competitive economics compared to alternatives, and since CO2 separation is already used as a part of certain production routes, such as ammonia production. We do, however, see a role as well for production based on electrolytic hydrogen, directly electrified steam crackers, and bioenergy. For steel, the technology split is more distributed. We see a major contribution from hydrogen-based direct reduced iron and also from carbon capture and storage applied to natural gas-based direct reduced iron, innovative smelting reduction concepts, and retrofitted blast furnaces. We also see a considerable role for iron ore electrolysis. For cement, carbon capture and storage is the overwhelming winner. This is because 2/3 of emissions are process emissions that cannot be avoided through fuel switching alone. Kilns running on electricity and smaller shares of hydrogen also contribute. However, due to the characteristics of cement production, their uptake remains relatively small and in most cases is applied in tandem with CCS to address process emissions. An area that we have been working on this year at the IEA in the context of the G7 industrial decarbonization agenda is developing definitions for low and near zero emission steel and cement production. This can help establish a shared vision on the future for key production processes in heavy industry sectors and can underpin enabling mechanisms such as public and private procurement initiatives and regulatory measures. I'd invite you to take a closer look at our G7 report, available freely online if you're interested in further details. It is evident then that there is much work to be done, and it is also clear that time is of the essence. Industrial equipment like blast furnaces and cement kilns tend to be long-lived and capital-intensive. The typical lifetime of these assets is around 40 years globally. When we take into account the latest refurbishment, we estimate that the average age today is around 10 to 15 years old globally, so these assets are only around 1/3 of the way through their lifetimes. Without any alteration to their current mode of operation, we estimate that existing heavy industry assets could lead to around 150 gigatons of CO2 emissions if operated until the end of their typical lifetimes. Just the emissions from these assets, leaving aside any capacity additions and replacements, exceeds the sector's net zero by 2050 scenario emissions trajectory. However, it's not all bad news. Changes can be made to this existing capacity, including incremental energy efficiency improvements, blending in of low-carbon fuels, and retrofitting with carbon capture and storage. Additionally, there is an opportunity presented by the dynamics of investment cycles, whereby every 25 years or so, a plant operator will face a decision whether to renovate or extend the life of key capital-intensive assets. If these investment cycles are strategically considered and new low-carbon innovative technologies are ready in time to replace existing assets when these investment decisions arrive, we estimate that around 40% of emissions from existing heavy industry assets could be avoided. So, how are we doing? We've just released our 2022 update of the IEA's annual Tracking Clean Energy Progress. In this publication, we look at 55 components of the energy system, technologies, sectors, infrastructure, and mitigation strategies, and assess their progress towards achieving the short-term milestones for 2030 laid out in the Net Zero by 2050 scenario. Of the 55 components, only 2, electric vehicles and lighting, are assessed as on track. This is the green traffic lights that we see on the slide. For the industry sector, almost all components are not on track, shown by the red traffic lights. Now, we're not saying that there's been no progress. In fact, quite the opposite. Recent technology developments and policy actions suggest momentum is accelerating in some important regions and sectors. For example, initial estimates point to 2022 being a record year for renewable electricity capacity additions, with an increase of about 340 gigawatts, roughly equal to the entire installed power capacity of Japan. And the pipeline for both hydrogen projects and carbon capture and storage facilities continues to expand. In the industry sector, last year we reached an important milestone with the first fully fossil-free hydrogen-based steel delivered at the pilot scale. We are now seeing increasing commitments from governments and the private sector for procurement of low-emission materials, and recent policies such as the US Inflation Reduction Act, Repower EU, and Japan's GX Leave will provide important supports for the industry transition. Still, much more is needed and at a faster pace across all regions of the globe to get the industry sector on track. So how do we accelerate the industry transition? Not surprisingly, there is no one quick fix policy or solution. Rather, coordinated efforts on multiple fronts across a diverse range of stakeholders are required. This includes governments and industrial producers in a leading role with valuable contributions from many other stakeholders. The overarching driver of change lies in setting long-term plans and establishing a clear, reliable policy signal for emission reductions, as well as aligning incentives to mobilize the finance and investments needed for clean technologies. Here, governments will play a key role by formulating transition plans and roadmaps, adopting long-term emission reduction policies such as carbon pricing or industry CO2 performance standards, and helping mobilize private sector finance. Additionally, targeted efforts are needed for specific technology categories, including emissions-intensive technologies that will still be required for some years to come, and clean technologies that are at varying stages of development today. Industrial producers will need to make careful plans for their existing assets and the timing for the rollout of new lower emission technologies. Both public and private sector efforts are needed to help create a market for near zero emission materials such as steel and cement, which may initially be more costly than when produced with conventional technologies. Policies options here include carbon contracts for difference, public procurement, and minimum content regulations. Innovations is still needed on technologies that are not yet market ready, which will require efforts of industrial producers and government support to pilot and demonstrate these technologies. With regards to material efficiency, efforts from actors along value chains from design to end of life will be important. Governments can support these efforts through modified design regulations that consider full life cycle emissions and that promote longer lifetimes where advantageous, and through setting up improved scrap collection and sorting channels. Finally, enabling conditions need to be put in place to support the technology transformation. Ensuring a level playing field for industrial producers around the world will be vital. Options here include sectoral agreements, industrial alliances, carbon border adjustments, or consumption-based emission reduction policies. These also come with challenges that would need addressing through careful policy design and rigorous CO2 content tracking schemes. International cooperation in other areas will also be important, such as technology co-development, best practice sharing, and international finance. Many of the near-zero emission industrial technologies require supporting infrastructure, such as CO2 transport and storage for CCUS-based routes, and near-zero emission electricity generation and hydrogen production for hydrogen-based routes. Since this infrastructure likely won't be used by one industrial producer alone, but rather multiple users, government planning and support will be needed. Also, it is important to start the planning early so that infrastructure will be ready for when near-zero emission industrial technologies reach the market. Finally, improved data collection, tracking, and reporting will also be invaluable for tracking progress and for differentiating near-zero emission production for policy and purchasing purposes. Time is of the essence, and we are now only one investment cycle away from a target of drastically lower CO2 emissions for industry. But the transition cannot happen overnight, which is why the next decade, from now to 2030, is a critical window to lay the groundwork that is needed for long-term success. This includes governments putting in place the necessary policies and supporting mechanisms to accelerate the transition, as well as industry commercializing and beginning to deploy near-zero emission production. There are some positive movements happening already within companies, countries, and at the international level, but we must accelerate this and move increasingly from discussions to on-the-ground action. With that, I'll conclude my presentation, and I would thank you very much for listening.